Hello, and welcome back to the course on Physics for Engineers. So before we proceed, let us review the previous topics. So in your linear kinematics, or motion in a straight line, you have these three concepts. You have the concept of displacement, final position minus initial position, the velocity, which is just displacement per unit time, and the acceleration, which is just the change in velocity per unit time. So in this lesson, we will now try to relate the linear kinematic quantities to the angular kinematic quantities. What are the equations that relate these quantities? So let's first relate linear versus angular displacement. So if you have a rotational motion, it will actually have a linear displacement or linear position, and that is given by the arc length of the circle subtended, or the arc subtended by your circular motion. So the arc length vector is related to the position vector by the radius vector. So its magnitude is r times theta. So this is the radius vector r. The theta vector, if you will recall, the theta vector is actually out of the plane or out of the page, so going towards you. That is the theta vector. So if you take the cross product of that, theta going towards you, and then this is r. So theta cross r is s. So basically, the s vector is always tangent to the circle. This is the s vector. So it's always tangent to the circle, theta cross r. But as of that, don't concern yourselves with the cross product. Okay. So this is the relationship now between the angular position and the linear position. So S is the length of this arc here, subtended by the angle theta. Now, if in any equation, this is a very important reminder. In any equation that relates linear quantities to angular quantities, the angles must be expressed in radians. So please take note of this. The angles must be expressed in radians. So if you want to use this equation, for instance, to find the length of the arc subtended by this angle theta with radius r, then this is the correct formula. This is wrong. Do not use degrees. So you must use radians. So of course, if you have the total arc length is when theta is equal to 360 degrees or 2 pi. So in that case, the total arc length is 2 pi times r, or 2 pi r, which is just the circumference of the circle. So the total arc length s for theta is equal to 2 pi is just the circumference of the circle, 2 pi times r, or r times 2 pi. Okay. So let's now relate linear and angular velocity. So the angular velocity is related to, again, the tangential velocity. By the way, the arc length vector can be expressed as a tangential position. So this is now the tangential velocity, and it is equivalent to the cross product of the angular velocity and r. So you're now seeing the pattern here. In order to get the linear quantity, just take the cross product of the angular quantity with the radius vector. So that's the pattern actually. So of course, the magnitude of a cross product, I forgot to emphasize this in the previous slide. The magnitude of a cross product is the magnitude of the first vector, the magnitude of the second vector, so omega and r, or r and omega, sine of the angle between them. So what's the angle between them? So in this case, the angle between them is actually 90 degrees. Sine of 90 degrees is 1, so that is now the magnitude of this cross product. Okay, so this is the r vector, if you will notice, and your omega vector is actually out of the plane, perpendicular to this plane. So you take omega is up, then r, so you will get v. So v is always tangent to the circle, or tangent to the path of the say object, or tangent to the path of this point P here. So direction is tangent to the circle, so same direction as, or the same direction as rotation. So how about linear acceleration A and angular acceleration alpha? So you guessed right, it's just alpha cross r. The tangential acceleration is alpha cross r. So the magnitude of this again is r times alpha, or alpha times r. But when you describe, when you discuss about uniform circular motion, there is actually another acceleration. So that acceleration is what we call radial or centripetal acceleration, v squared over r, or omega squared r. So therefore, if an object is moving in a circle, it can, or it may have, or it can have two types of acceleration: an acceleration that is tangent to the circle, and an acceleration that is towards the center of the circle. That is the radial or the centripetal acceleration. It's towards the center of the circle. And therefore, the total acceleration is just the vector sum of these two, the tangential and the radial acceleration, with the magnitude of this one, given by Pythagorean theorem. So the total acceleration is just the square root of the tangential acceleration squared plus radial acceleration squared. Okay. So, by the way, when you discussed on the topic of uniform circular motion, you assume there that there was no angular acceleration, meaning the tangential linear acceleration is 0 in that case. So you only have an object that's moving with uniform velocity. So let's now have an example. Okay, so all segments of a rotating fan blade have the same angular velocity. So for the first question, compared to a given blade segment, how many times greater is the linear speed of a second segment twice as far from the axis of rotation? So for instance, we consider two segments of the fan here. So say this segment here, and say this segment here. So the first segment is has a radius, say r, and the second segment has a radius 2r, twice. So twice as far from the axis of rotation. So our axis of rotation is the center of the blade. So the question is, how many times greater is the linear speed? How many times greater is the speed here, the speed in the second segment, as compared to the speed in the first segment, say v1? So we just need to compare the linear velocity of the second segment and the linear velocity, or the tangential velocity of the second or the first segment. Okay. So for letter A, for segment 1, v1 is equal to, its radius is r, and its angular velocity is omega. That is v1. How about v2? The velocity of segment 2 is just the radius, or the distance from the axis of rotation, which is now 2r, and its angular velocity. In this case, the two segments have the same angular velocity. It must have the same angular velocity, or an angular displacement, because if they don't have the same angular displacement, then one segment will be much faster than the other, and that is not the case for the rotating fan blade. If that happens, then your rotating fan blade is already very dangerous, or it's already getting destroyed if that's the case. So they will always have the same angular velocity. So for one single rotating body, all points of that rotating body have the same angular velocity. But they don't have the same linear velocities because they have different distances. So the first segment has a distance r from the axis of rotation. The second segment has a distance of 2r. Now, if you write this in terms of v1, sorry, r and omega, r omega is v1. So basically, this is just 2 v1, where r times omega is v1. So this is not the answer for letter A. So the second segment is actually has twice the velocity of the first segment. So for an electric fan or ceiling fan blade or any rotating fan blade, be careful not to touch the tip of the fan because that has the largest tangential velocity. So if you touch that one, then you might get cut or you might get injured. So technically, it's safe to touch the center of the fan blade. At the center of the fan blade, that is at r is equal to 0, basically doesn't have a velocity, zero velocity. It has the smallest linear velocity, the center of the fan. So that one. So don't touch the edge of the fan. So this implies that as r becomes greater, the tangential velocity also becomes greater. Now for letter B, how many times greater is the radial acceleration? Okay. So for the first segment, its radial acceleration is omega squared. We have the same angular velocity times its radius, which is r, or distance from the axis of rotation, which is r. For the second segment, so they have the same angular velocity, but sorry, this is not the way. We'll use the velocity equation. Sorry. So you will have v1 squared over r, v squared over r. Now for the radial acceleration of the second segment, you will have v2 squared over r. But v2 is twice v1, 2v1 squared over r. So you will get 2 squared, so you will get 4, then v1 squared over r. v1 squared over r is your a1. So basically this is 4a1. So a2 here is 4a1. So the radial acceleration of the second segment here is actually 4 times the radial acceleration of the first segment. That's because the radial acceleration depends on the square of the velocity. So if the velocity doubles, such as this, the acceleration will actually become 4 times, quadruple, because that is 2 squared. So it's basically an example of ratio and proportion. So moving on to another example. Oh, sorry, that's too fast. Previous. Okay. An object is moving in uniform circular motion with radius 1 meter at a velocity of 3 meters per second. So if the total acceleration of the object is 5 meters per second squared, what is its angular acceleration? So in this case, the object is moving with uniform tangential velocity, but its angular velocity is not necessarily uniform. In fact, it's changing because you're asked to solve for the angular acceleration. Okay, so this is an example of an object which has a radial acceleration, v squared over r, and it also has a tangential acceleration, r times alpha. So from the equation for total acceleration, so I'm just going to use the square part. So you have the total acceleration is just the radial acceleration squared, so Pythagorean theorem. So the square of this, you have v the fourth over r squared, square of that, plus the square of that one, so r squared alpha squared. Okay, we are given the total acceleration of the object, a total. We are given the uniform tangential velocity. We are given the radius, 1 meter. We are asked to solve for alpha. So this is now solvable. Only one unknown in this equation. So I will leave the derivation to you. You will get alpha is equal to square root of v to the fourth over r squared minus a total squared over r. So you substitute all of the values, and you will get an answer of 7.48 radians per second squared. Okay, I forgot to emphasize. If you are working from angular to kinematic, sorry, I'm just gonna angular to linear. Sorry, angular to linear quantities, you need to drop the radians na unit. You need to discard the radians na unit. But for the reverse, from linear to angular, you need to add. You need to add the radians unit. So please take note of this. So actually here, all of the givens here have no radians. So if you just use the initial units, you will get a value of 7.48 over second squared. So we just added the radians unit here because we are looking for angular acceleration. So in the formulation of equations, we usually don't include the unit of pi. So pi supposedly have a unit of radians, but in our derivations, we don't include the radians unit. That is why we have to add the radian units here. But in order to solve that, just take note of this. You're going from angular to linear quantities. Drop the radians unit. You're going from linear to angular quantities. You add the radian units. So here we are going to the angular, because this is angular acceleration. Okay. So for another example, we have a bicycle. So how are the angular speeds of two bicycle sprockets related to the radius and number of teeth of the sprocket? You know what's a sprocket, right? The gears. It's basically the gears in your bicycle or motorcycle. Okay, so these two sprockets are actually not rotating at the same angular velocity. The rear sprocket, say, I will R na lang, no? It's in the rear, has an angular velocity of omega r, and it has a radius of r, say rf, or r sub r, the radius of the rear. So the front, on the other hand, has a different radius and has a different angular velocity. So you have the angular velocity of the front, and the radius is rf, the radius of the front. Now, what they have in common is they have the same tangential velocity because they are connected by this chain here. And this chain will actually not slip. It will actually roll or rotate without slipping. So this chain will rotate without slipping, because if the chain slips, that's already a problem with your bike. Maybe your teeth are now needs replacement, or your gears are now needs replacement. Now, since the chain here, the links in the chain are equidistant, have the same distance, and this chain will actually what do you call this? This will actually touch the teeth. So actually the teeth of the sprockets will actually go or intertwine with the chain, with the links in the chain. So that means the number of the distance between the teeth here and the distance between the teeth of the rear and the front sprocket must be the same. They are the same as the distance of the chain links. So in that case, the number of teeth is proportional to the radius. The number of teeth n of the rear sprocket over the radius of the rear sprocket, this ratio must be the same as the front. The number of teeth in the front sprocket must also be over the radius of the front sprocket. These two ratios must be the same because the distance between the two teeth are the same. So this is the relationship now between the radius and the number of teeth. Okay, so in the problem, we're asked to find the relationship between the angular speed of the relationship of the angular speed between the radius and the number of teeth of the sprocket. So you will notice here that n of r is just equal to cross multiply. So you have r of r over rf and f. So nr and r. So n is actually proportional to r. The number of teeth is proportional to the radius. The larger the radius, the larger the number of teeth. The smaller the radius, the smaller the number of teeth. Okay. So how about the angular velocity? So they have the same angular velocity v. For the rear, so this is actually equal to the radius of the rear times the angular velocity of the rear. But this is also equivalent to the radius of the front times the angular velocity of the front because they have the same linear velocity v. So we can now have the relationship between the radius and the angular velocity. So the radius of the rear is actually omega f over omega r rf. So I just divide by omega r. So you will notice that r is inversely proportional to the angular velocity. So smaller the radius, the larger the angular velocity. So in this configuration, where the front gear has the larger radius, it actually has a slower angular velocity, while the rear has a larger angular velocity. So most bicycle types or most bicycles are designed this way. But you also have mountain bikes, which can have different gears in the front and different gears in the rear. So you can actually reverse the radius ratio. You can actually make, for a mountain bike, you can actually make the radius of the front sprocket smaller, and you can actually make the radius of the front rear sprocket larger. And you use that configuration whenever you go uphill or downhill. So when you go uphill, so since the front sprocket has a smaller radius, it will rotate at a faster angular velocity. And then when you go downhill, the same thing. So when you go downhill, it's not advisable that the speed of the bicycle depends on the speed of the rear wheel. So it all boils down to the rear wheel. So when you go downhill, it's not advisable that the angular velocity of the rear wheel must be very fast. It must be as low as possible to prevent accidents. So usually when you go downhill or uphill, your rear sprocket has a larger radius compared to the front sprocket. So from here, since we can actually solve for RF in terms of this one, in terms of the number of teeth, so RF is actually the radius of the front, so can actually be written as NR over NF. Sorry. It's the reverse. NF over NR. R sub R. So you can substitute this value here to obtain the relationship between the number of teeth and the angular velocity. So this is actually the result. So the number of teeth is actually inversely proportional to the angular velocity. So the lower the number of teeth, the larger the angular velocity. Because if you have small number of teeth, meaning you also have a small radius. And a small radius means larger angular velocity. So that one. So it's basically just an analysis problem. Okay, so that is now the last example for this lesson. So that is now the end of the first part of chapter 6, which is all about angular kinematics. So in the last two chapters of the last two lessons of this chapter, we'll be focusing on the dynamics of rotation. So I will see you again in the next lesson.